These next two inequalities, one is actually a linear inequality, and the reason I call that is because if we graph this function and we graph this function, they're both lines. So we're basically comparing when does one line, right, when is it above the other line, and then this obviously has an absolute value. We're actually going to look at some other strategies when we go back to 1.7, and we'll figure out some other ways to do this. But what I just kind of want to prove is that I've given you an option. I've given you something that actually works all the time. So I'm going to go ahead and use our 5.6 strategy to solve these, and then we'll go take another look at them using a 1.7 strategy and see that we have the same thing. So you've got one method that works all the time no matter what: linear, absolute value, polynomial, quadratic, rational. It works, right? It's labor intensive, but it works. But then lines, absolute values, and quadratics we'll visit 4.5, have some little nuances that we can take advantage of and learn from as well. So that's why I'm kind of, again, seems like I'm backwards. I am, because I'd rather show you something algebraically that works all the time. You can use it all the time, and then we can look at the nuances for lines, absolute values, and quadratics in some other sections. So at any rate, right, what's the first move here? What makes me undefined? Well, nothing, right? There's no division by zero. What makes me equal to? So putting these things equal to each other and start solving, I'll subtract 3x from both sides, subtract 5 from both sides. We get a negative 5x equals a negative 7, right? Dividing both sides by negative 5, we get x equals 7/5, or 1 2/5. So we have one value that makes us equal to. So I'm going to come to my number line, right? I know 7/5 is on the number line somewhere there. So my behavior, right, is to the left or to the right. So we just have to test intervals. So testing the intervals, x equals 0 is available on this side. So when I plug that in there, 5 minus 0 is basically 5. Is that greater than 0 minus 2? And the answer to that is a resounding yes. All right, that is true. 7/5 is 1 2/5, so how about we throw a 2 in there? So 5 minus 2, well, that's 5 minus 4, which gives us a 1. Is that greater than? Well, 3 times 2 is 6, minus 2 is 4. Well, that's a resounding no. That does not satisfy. So putting this all together, right, we are not allowed to be equal to, so we're going to be open at 7/5, and then we're basically going to color, right, that part of the axis, because that's what made the inequality true. So my solution is from negative infinity all the way up to 7/5, right? And that is what makes this situation true, all right? And of course, what we can do, right, is we can go ahead and compare the two graphs. So using my Desmos, there's 5 minus 2x, and here's the graph of 3x minus 2, and you can see the intercept we know is occurring at 1 2/5 or 7/5, and the graph of 5 minus 2x does seem to be, or it is above, right, the graph of 3x minus 2 to the left of 7/5. Of course, when we go to the right of 7/5, the graph of the other one is above, so that's why there was a no there. So our graph visually shows what we have for the other one. Again, the absolute value graph, the strategy remains the same, right? So what makes us undefined? Well, nothing, right? There's no division by zero. What makes us equal to? We basically have to satisfy, right, the absolute value. When does that equal to each other? If you guys remember, for absolute values, and we solved them a long time ago, we break them up into two pieces, right? We're either equal to negative 2 or we're equal to positive 2. And so here we'll add 4, and we get 3x equals 2. So one of our values is 2/3. Here we'll add 4, divide by 3, and we get x equals 2. So on my number line, right, we have 2, and then we have 2/3. So we have 3 intervals, right? And by the way, we're allowed to be equal to, so these guys, right, since they satisfy the equality part, I'm going to go ahead and put a closed dot on them because equality is allowed. So when are we greater than 2, or when are we less than 2? We start testing intervals. So x equals 0 is available over here because 2/3 is to the right of that. So when I plug that in, 3 times 0 is 0. We get the absolute value of negative 4. Is that bigger than 2? Is 4 bigger than 2? Yes. Okay, that is a true statement. X equals 1 is available here, so 3 times 1 is 3. Take away 4 is negative 1. Is the absolute value of negative 1 bigger than 2? Is 1 bigger than 2? Of course not. Right? So no. And then, actually I shouldn't circle it because we don't want that. No. And then 2, well, when x is 3, right, that's bigger. So 3 times 3 is 9. So we have the absolute value of 5. Is that bigger than 2? Is 5 bigger than 2? And the answer is yes. So putting this together, right, we're talking about things being on that interval. We're including 2/3. We're including 2. And we're talking about things being on that interval there. So my solution is negative infinity to 2/3 union 2 to infinity. So there's my solutions for that particular inequality. Again, we can test that by looking at my Desmos, and it looks like I'm getting a phone call, so let me ignore that. So when I go to Desmos and I basically graph 3x minus 4, right? There's what that graph looks like. So there's 3x minus 4, and I want to know when it's basically sitting below the graph of 2. So hopefully that'll graph that. There we go. Right, and so you can definitely see, right, we know this to be 2/3, and we know this to be 2, and the graph of the absolute value does sit below, right, the graph of those. So we want to know when it's above the 2. So that's this interval here to the left of negative 2/3, and we want to know when the graph is above 2, and that happens when 2 to infinity on that interval. So basically our graph again supports the algebra that we're doing. So that wraps up 5.6. Again, the strategy for all of these is step 1 is to solve what makes us equal to and what makes us undefined. That gives us some numbers that we can graph on our x-axis, our number line. Step 3, we start testing intervals in the inequality. What makes the inequality true or false? Shade the regions that make us true. Color, use what makes us equal to or undefined. We use closed dots or open dots depending on the situation. Step 5 is to put it all together and put our answer in interval notation. And if you've done everything right, those intervals are pretty easy to see. We just basically rewrite it in interval notation. So there's your strategy. Again, this inequality strategy works for all inequalities. It's something that works all the time, no matter if we're linear, we're absolute value, we're polynomials, we're rationals. It doesn't matter. Even when you start doing sines and cosines and other things, this method works. Labor intensive, but it works. All right, so we're going to go back in time now. We'll go visit 1.7 and look at some nuances of lines and absolute values. We'll go back to 4.5 and look at some nuances of some quadratics. And I'll see you guys in those videos coming soon when we jump into those sections. Talk to you guys later.